Okay, so today we're going to go over arc length, and that's basically just the length of a smooth curve. Now, in They Do Now, we went over finding the length of different functions on a closed interval, and one of them was a line. And we've been looking at different problems where we're saying, find the area between these two curves. And it turned out one of them was an actual line. Well, it's easy to find the length of a line on a closed interval because you can just use the distance formula. No problem. Now, you also saw another equation, and if you graphed it, it's a semicircle. So the length of this is using circumference, okay? Or I should say half the circumference of a circle. And so for that curve, we're able to find the length of it. However, not every curve that we see in the coordinate plane are we going to be able to find the length by using a formula that we've learned from previous courses. So in this course, we learned another one, okay? And you can see in the picture here, hopefully you're already copying it down, that we have two different formulas. It's actually essentially the same one, okay? And let me read this to you while you're copying it down. So if a smooth curve begins at AC and ends at BD, so two different points, where A is less than B, if you want to say less than, and C is less than D, then the length or arc length of the curve is, okay, so let's go through the first formula. Okay, so it might be really, really small there. I'm going to write it slightly differently on the side too, so that way you can double check to see if you wrote that correctly. So length is the integral of the square root of 1 plus dy over dx, which is actually our first derivative. So I'm going to call that f prime of x, okay, squared. I have too long of a expression there. Okay, so it's the square root of that with respect to x, because we're going to integrate, and we're going to integrate from a to b. Okay, because those are the x values or x coordinates, okay, of the 2 points that are described. Okay, so now this is if y is the smooth function of x, so that's why in the parentheses I wrote f prime of x, and it's on that closed interval, once again, from a to b. Now, again, hopefully you had a chance to write down the second part of this, and if you're missing something or you're not quite sure what this is, don't worry, I'm going to write it for you so you can double check. So L is equal to, means length, the integral, the square root of the quantity 1 plus dx over dy squared. Well, the reason it's dx over dy squared is because we want to say f prime of y. So sometimes we may have to integrate with respect to y. I'm sorry that f is a little sloppy. Let me fix that. I guess I'm going to fix the whole thing. Okay, sorry. And that's okay. We're going to need the y values. So that means we need the y coordinates. So that means it's going from C to D. Okay. So it depends on what the problem is, how we would approach it. Do we want it f prime of x? Do we want to integrate with respect to x? Or do we want f prime of y? We want it in respect to y. So generally, if your equation's like y in terms of x, then you're going to use this one. And if it's x in terms of y, you're going to use, that's supposed to be a y, this one. Okay, so now that it looks like I'm going around and around in a circle, let's actually see how this formula can be used in an example. Okay, so hopefully you had the chance to write down number 1. If not, I'm going to read it as you write it down. It says, find the exact length of the curve, and the curve is defined by y equals 4 square root of 2 over 3 times x to the 3/2 power minus 1. And this is going to be for the interval defined by 0 is less than or equal to x, which is less than or equal to 1. Okay, so the first thing that we want to do is be able to set up an integral that represents the length of the curve defined by our function on that interval. So in order to do that, we just learned in the formulas we're going to need the derivative. So let's call this equation f of x, and that way we can find the derivative. So f prime of x. Okay, so we're going to need to do our power chain rule here and the difference rule. So going back to some older stuff here. And it's going to simplify to be 2 radical 2 x to the 1/2 power. Okay, all by itself. The derivative of -1 is 0. So now we have f prime of x. So what would be the exact length? So we're going to say L is equal to the integral of the square root of 1 plus, okay, our 2 radical 2 x to the 1/2. But now this is being squared. Don't forget the parentheses, very, very helpful, with respect to x, and we're going from 0 to 1 in this problem. Okay, so now we can do a little bit of simplifying here, which is a really awesome thing for this particular problem. So if you take a look at what we're squaring, okay, we're going to square the 2 radical 2, okay, so that's going to be 4 times 2, and that's 8. And if we have x to the 1/2 power, and that's raised to the second power, that's going to be 1/2 times 2. That's 1. X to the first. Okay, so now we have this expression here, which is a pretty awesome expression that we could work with, because we can actually find the antiderivative for this with u substitution. Okay, now many times you're not going to be able to simplify it down and find the antiderivative. Okay, you're not going to be able to use u substitution or integration by parts. So I would say that at this particular place, you would then use, if you cannot integrate, use the graphing calculator. That's why we went over it, and there's been other problems where it popped up that we need that graphing calculator to evaluate our definite integral. Okay, so let's get back to our problem, because we didn't need the graphing calculator here, but we do need to finish this. So if u is 1 plus 8x, then du would be just 8dx. So dx would be 1/8 du. Now you could also replace the values for u if we leave it in terms of u. So if u is 1 plus 8 times 1, then u becomes 9. And if u is 1 plus 8 times 0, my lower limit of integration is 1. My upper limit is 9. So that way we can change our we could change our, I want to say indefinite. We want to change our definite integral. So let's do that. Let's start at the top again. Okay, so who knew that it would be a tongue twister? No, not really. Just maybe a little bit of excitement to finish this off. So I'm going to replace everything with u. I could also, let me not write the integral yet, I have a 1/8 du. So let me take out the 1/8 before the integral. And my lower limit of integration is 1. My upper limit's 9. And we have u to the 1/2 power du. So in this particular case, we can find the antiderivative here very easily. So we're going to have 2/3 u to 3/2 power. And we can plug in 9 and 1. Actually, we can pull out the 2/3 and multiply with 1/8. That way it'd be 1/12. That makes it a little bit easier to use. So we can plug in the 9 and plug in the 1. Okay, and remember power over root. So I can take the square root of 9. Okay, so it's very easy. It's 3, and then 3 cubed is, let me change color here. 3 cubed would be 27. Okay, and the square root of 1 is 1, and 1 cubed is 1, or just, 1 to the 3/2 power is going to be 1. So we end up with 26/12, which we can obviously simplify a little bit because 2 goes into both. So we can say that the length of this curve from 0 to 1 is actually 13/6. Okay, and I'd probably say units there, but just leave it as 13/6. Now, once again, if you did use the graphing calculator, you're going to get like an approximate value typically. So just remember to approximate to 3 decimal places. Your answer always to 3 decimal places. All right, so hopefully you kind of understand the formula of arc length, how it could be used, and I'm going to actually go into where the formula kind of came from so you have some more background information on it. But at this point, you're done with the practice, or I should say the example. You can move on to the practice. You can stop the video, but if you'd like to see how it kind of came about, you can keep watching. Okay, so I'm going to do my best to explain how the formula was derived. So I'm doing number 2 now. So let's talk about our curve and our coordinate plane. Okay, so let's say we have a curve. We want to find the length of it on the interval from A to B. All right, and I'm going to say that this point A, its y value would be C, and this point B, its y coordinate is going to be D. So it kind of ties into our formulas that are listed over here. Okay, so what you can do is kind of break this up and look at different points along the curve and connect them as best you can with line segments. Okay, not very good at connecting them with line segments. They should be straight lines. But we can easily find the distance of each line segment by the distance formula. So what you would need to do, okay, so take any 2 points, okay, is find out the distance from the 2 points, okay, this way. And in this particular case, I don't know where these points kind of lie, and they are going to be like certain x values. Now, we used, with Riemann sums, x sub I minus 1 over here, okay? And I think since you're familiar with that, I'm just going to stick with that and x sub I. So the distance between them, I'm going to label that as delta x sub I. okay? And then you also need the distance, okay? I'm going to change my marker color here, going up, and that is not the change of x, but the change of y. And it would also be of sub I, okay, because it's referring to the x values that you're plugging into this function, okay? And that function, let's call this f. Okay, so this would be f of x sub I minus 1, and this would be, it's not supposed to be a d, f of x sub I. All right, so now that we have those two expressions, okay, to measure out what we would say like the x and a y, remember the distance formula? This is square root of the change of the x's, okay, or x sub 2 minus x sub 1 squared plus the change of the y's, or the y sub 2 minus y sub 1 squared. Okay, so now we have a whole bunch of these, okay, that we keep using along the way. And the more that we have, the better approximation we would end up. So let's start taking a look at if we added up all these line segments, and now my curve is getting a little sloppy, but maybe a little bit clearer as I keep putting in more and more line segments, we're getting the length of it, okay, because we want to go from here to there. So we're going to add up all the line segments, okay, that we can possibly have between there. So we want to add up all the distances, okay? And I don't really need the parentheses. We'll just try to be as careful as we can when we're writing this. Okay. So now we're talking about using summations, okay? And we know that with arc length, our formula did deal with a square root, and we already see one there. And you may remember by using Riemann sums to approximate the area under a curve bounded to the x-axis. It was the sum of all of our rectangles, or trapezoidal rule even. You're adding up all the trapezoids. So that sum is going to end up being our definite integral that we have. So now, if we're dealing with a definite integral, we always like to write whether we're working with dx or dy. You may remember in Euler's method that the step size can be written as delta x or dx. So if, let's say, I'm trying to use this or derive this first formula here in terms of x, I would want to establish dx over here on the outside. So I want to actually factor out a delta x, okay? And the only way I could really do that, because it's stuck underneath the square root, I want to factor away from this expression a delta x squared. So let's do that. So if I factor out a delta x squared, it's delta x sub I, but it's like a square, and I'm going to end up getting 1 plus a delta yi over delta xi, and I can leave these as a square, or I could just write it as 1 square on the outside. This is the same expression, guys, okay? If this is squared and it's over this squared, okay, it's the same expression, okay, same thing. So I don't need this up here, so let me erase it. And you might be able to see now, over here, I could take the square root of each factor. Well, the square root of this is just going to be my delta x, okay, sub I. And I'd still be left with the sum square root of Now, what's over here? 1 plus my delta yi over, I'm sorry, my triangles aren't coming out very good down there, delta x sub I squared. Okay? So I needed some room, so I erased the stuff at the top so I could kind of like use the space up here. I didn't need it. So once again, that delta x sub I, that's going to be like our dx. Okay? And let's take a look at our sum. Right? So we end up adding up all of these line segments. Okay? And the way in which we can add up an infinite amount, we would write limit, but I don't want to write the limit of the sum once again, okay, for all of this. So I know that I can use a definite integral and it's going to be the same thing. So let me start writing my definite integral because it ties in with that dx. I don't want to leave it by itself. So this, the rest of it, okay, that we need to talk about, because it's not just the sum of like delta x sub I, it has that square root. It's going to be this integral of the square root of 1 plus, okay, look at this description here. Change of y over change of x. All right, so this is basically what we have for dy over dx. So I'm going to write that as a square. And we're doing this from whatever the x values are because it's in respect to x. So in this particular case, I got from A to B. So I have all of these line segments added up. So the exact way to write is by definite integrals. Now, take a look at that definite integral, okay, that we're trying to evaluate. I need more space, of course. And there's no problem from like A to B, okay? Square root 1 plus, fine. That dy over dx is exactly what's written here, and that is our derivative, okay, f prime of x. And that is why this is squared. We can take it with respect to x. Now, once again, we can do this whole procedure again, okay? And instead of factoring out an x sub I, we can factor out an a delta y sub I squared instead. And what's going to happen when I factor that out instead, I'm going to get 1 plus, okay, change of x sub I over change of y sub I over here. So if you look at that, that's the same as, I need an eraser. I'm going to use this space here. This is the same as dx over dy. Okay, and that would be the same thing, not as f prime of x. This is going to be f prime of y. So that's how you can end up redoing this whole thing for deriving where it's in respect to y. And you have an equation, not maybe y in terms of x, but x in terms of y. This comes in handy in future problems where maybe your function has some sort of vertical tangents. Then you want to integrate with respect to y, because this will be defined, this will be 0, whereas dy over dx is something that's undefined. So that's what happens with a vertical tangent. So you may want to use this instead, because it's okay if your slope of your tangent line is 0. We'll talk about more about vertical tangents, corners, cusps, all the places where your function may be non-differentiable in the next lesson. So stay tuned and good luck. I will see you soon.